I was trying to describe a few research topics that students can start thinking about. And so we tried various directions. I think I spent 2 lectures on your, three lectures on your paper, and we did something. So it's very good that I speak in a seminar including you as in the audience. So
yeah, I can't wait to hear it. Actually, we should probably get started 5 after, right?
Well, after you. I like this very relaxed atmosphere. So
okay, I'll give you a little introduction now. So yeah.
Okay.
All right. So welcome everyone. Today we have Jian Ding from Peking University. Jian did his PhD in Berkeley in 2011, and then after that he did a postdoc in Stanford, and he had tenure track positions at the University of Chicago in the statistics department and the Wharton School at the University of Pennsylvania. And he just recently has moved back to Peking University, where he did his bachelor's degree. He's got a number of accolades. He won the Rollo Davidson Prize in 2017, jointly with Nike's son. He this year gave an invited lecture at the ICM, and in 2024, he'll give an IMS medallion lecture. So we're obviously very pleased to have him speaking here. Okay, Jian, go ahead and you can tell us about shotgun assembly problems.
Okay, thank you, Nathan, for the invitation and for the very nice introduction. I apologize, I just noticed that Peking University is spelled as Peking University. I don't know why that happened, but it happened. It seems this is a fairly friendly crowd. Just interrupt me anytime that you have a question or you want to chip in with your insights or comments. I didn't prepare that much technical stuff. It's more like a chatting style of talk. Hope that you will enjoy, and hopefully I can also tell you a bit of what kind of progress we made following what Mossel and Ross proposed a few years ago. Okay, so let's start the conversation from some sort of a theoretical perspective. There is a, I think, fairly famous conjecture in combinatorics, which is known as the reconstruction conjecture. It says the following: suppose you have a graph, and suppose for each vertex you delete it, then you get a vertex deleted graph. Then you have n copies of this vertex deleted graphs. Each copy is like a card, as you can imagine, and it's illustrated in this picture. And I give you the deck of the cards, meaning for each vertex, I delete that vertex, and you get a graph. You have n copies of this. You want to see whether you can reconstruct the whole original graph from this deck. Of course, the card I give you, I mean, the vertex deleted graph I give you should not be labeled, right? Otherwise, it's trivial. Then you know which vertex is connected to which other vertices. The key point is that the card here is not labeled. Then can we still reconstruct the whole original graph up to isomorphism? So that is the question, and it states as a conjecture, meaning people believed yes. I feel that isomorphism is a concept that we should be familiar with, but just in case, let me quickly remind you. We say that 2 graphs are isomorphic to each other if there is a vertex projection between them, such that it also preserves the edges. For instance, in this 2 small pictures, these 2 graphs, although looking somewhat different, they are actually isomorphic to each other, and the vertex projection are given by the colorful vertex labels. So this is a small example of isomorphism. This conjecture is all deterministic. It's kind of from an extreme combinatorics point of view. It still remains widely open. I checked some survey papers today. There are some partial progresses, but I think widely open is still the correct summary for the status of this conjecture. we can also generalize this conjecture a little bit, because why we only delete one vertex, right? Maybe the information we can get is even more perturbed or even more local. So there is a generalized conjecture proposed in 50s by Kelly. It says for any integer k, there is a integer f of k, so that for any graph with at least fk vertices, it can be reconstructed from k vertex deleted subgraphs. You probably can imagine what is the meaning of k vertex deleted subgraph. You just choose k vertices, delete these vertices as well as edges incident to them. What remains is a k vertex deleted subgraph, and just go over with all choices of k tuples. And then you ask, can you recover the original whole graph after isomorphism? Naturally, fk has to grow in k, right? Otherwise, it doesn't make sense, because you could have deleted everything. Fk is small. But this is, as you can tell, since the previous conjecture is widely open, this is also open. As probabilists, then it's natural to wonder what if we introduce randomness to all of this, to all this business? For instance, what if the underlying graph is random? Then for this, we have a fairly satisfying answer, thanks to Belabes for his work in 1990, which says that almost all graphs can be reconstructed from any 3 vertex deleted subgraphs. So this says, since randomness helps a lot in terms of circumventing the extremely bad situations. And this also motivates us to consider some more ambitious questions, right? Removing 1 vertex or 3 vertices, the information we get, it's still global. It's like you have almost global information and you want to patch them together to get the global information. Okay, that's hard in general, which in general may be a misleading word. That's hard in the worst case scenario, but very easy in the random instance. So in the random instance, can we make the question even harder, but still having a meaningful solution? So we want to have very local information about the graph, and then we want to patch the local information together so that we can correctly recover the original graph. So that's the general philosophy for this topic. And here is a precise framework proposed by Mossel and Nathan Ross. A few years ago, the paper was published with the date of 2019, but I think the work has been circulated a few years before that. And it has been like maybe 7 years or something like that until now, and it has been inspired a number of studies in the mathematical community. So here is the certainly including us, and here is this framework. The model is we can take G as a fixed or random graph, and possibly with some random labelings on vertices. Okay, and then what is the observation? The observation is for each vertex, we observe the rooted neighborhood of radius r, but we do not observe identities of the vertices, because if we know this is the neighborhood for these vertices, then that's trivial. The key point here is for each v, we can take a local picture of what's happening around it, but then we don't know, basically you don't know where you took the picture. You just know, okay, you have this deck of pictures you just take to reflect the empirical profile of local information about this random graph. without knowing which picture is taken from where. And then you wish to patch together all these local pictures to have to get a global graph. Of course, we use the natural metric, which is the graph distance in this framework, but this can also be adapted if there is some other metric or some other choice of local neighborhood which would make sense for applications. Without any side information, it seems the neighborhood with respect to the graph distance is the most natural one, and certainly we mathematically we like it too. And then the question is, I think I pretty much have implied what is the question, but just let me state it explicitly. The question is, from all these local pictures we just take, or a bit more mathematically, from this collection of the local neighborhoods we have, can we correctly reconstruct the graph up to a label preserving isomorphism? For instance, here is an illustration. We have some graph, and if we take I equal to 1, we get 5 local neighborhoods, and then we put this into a possible lemmaty set. So there's no ordering on among these 5 local neighborhoods either. And the question is, if you do not see the graph on the left, you only see this set on the right-hand side, can we recover what happens on the left up to isomorphism? This illustration is a little too small, so it feels kind of similar to the illustration we see in the reconstruction conjecture, because that's just because when the graph is so small, deleting one vertex or take a neighborhood of depth 1 happens to be somewhat similar. But if the size of the graph is very big, you see these two are very different. Okay. These problems are not just of theoretical interests, they also have rich connections to applications. Actually, before Achner and Nathan proposed the mathematical framework for this problem has been around, I believe, in applied fields for some time, with interests from biology or others. One example is the DNA shotgun sequencing problem. We wish to recover the whole DNA structure. Basically, that's the permutation of ATGC stuff. But for some reason, the technology only allows us to get shotgun reads of the DNA. Well, at least up to some time point, that was the situation. Maybe things have been changed. Maybe now technology can allow to have access to better type of data. But for quite some time, that's what people can do. So naturally, we wish to. So what we get, the data we get, is these segments illustrated in this picture, and the idea is we wish to recover the whole sequence from this fragmental information we can collect. So this is one of the examples in application. Of course, almost like everything we do in theory, there is this application, there's this actual problem we work on, and usually there's some distance between them, right? At least at the start of the theoretical study, that's the case. I have no intention to pretend otherwise, and actually to study or first formulate mathematical questions that is more closely related to applications, or that can actually be applied directly to real problems, and say something interesting about it from a mathematical perspective, that's a very challenging and very interesting direction. That's not covered in this talk. So in this talk, we work on sort of toy models where we take idealistic mathematical model and try to prove theorems about them. I think it's a good starting point for this. This is just the illustration of what kind of shotgun reads we can get in a bit more precise way. So for instance, if we say that what we can read is the labels in a neighborhood of depth 1, then there's 6 short intervals are the observations we can get. Again, since the whole sequence is 6, this illustration is helpful in some ways, but also misleading. It would be more illustrative if I give you a much longer sequence, but you see that's not possible. From the perspective of drawing the picture. Oh, in the caption it says for shotgun assembly of labeled graphs by Ding. Okay, that's because my student, well, not my student, my co-author, who steals my picture and give credit to me, and I stole his slides without deleting my name. Anyway, so here is a more precise definition of the lattice labeling models. We consider a graph, which is just a box of size n in d dimension. And we have some random labels on the vertices. Of course, we can choose different distributions for the random labels. Actually, you want to choose the distribution that reflects to the application problem you have at hand. But without any actual reference to applications, I guess we can be convinced that IID uniform vertex label is a classical choice, and that's what we stick to. And the observation then is vertex labeling configurations for each R box in this big box lambda n. As I said earlier, we do not know the location of we do not know the location for each R box, and we take local pictures and don't know where the picture is taken. So this is one of the examples proposed in the very inspiring paper by Echner and Nathan, and they also proved that the correct order for the shotgun assembly threshold is log n. Basically, the idea is if it is log n with a very large constant, sorry, the log n is r to the power of d is log n, not r is log n. And we will see why it's r to the power of d should be log n. That's because if that's the case, the R box has volume log n, right? And if log n, if this volume comes with a large constant, then typically each R box should have a unique labeling configuration. If that's the case, it's easy to patch things together, because then you know, okay, this box should be followed with that one, because the labeling configurations is unique on each R box. Maybe in the actual proof, you need to use something slightly stronger, something like not only R box is unique, but also R-1 box is unique, something like that. But this doesn't change the asymptotic threshold anyway. This allows you to patch things together. If R is too small, then you can find sort of blocking constructions. So here is a, say, 2R box. here and two R box somewhere far away. Why we choose two R box? That's because if we change the labeling in the center, everything that will be affected happens in that 2R neighborhood. And if you pose some structure constraint on these 2R neighborhoods, that means swapping the centers, swapping the labels on these two centers will not change the R neighborhood profile, but certainly will change the global labeling profile. Even if you use things like up to isomorphism, there is not that much asymmetry in this problem anyway. So that is the basic idea of the work of Erdos and Nathan. What remains is to do probabilistic computations to say, okay, what is the threshold or what is the bound one can get to have things to be unique, and what is the bound on R that one can get so that we can find two R neighborhoods, which allows for such swapping I just described. So, Nathan, is this a good summary of what you did here? And then they made a conjecture in their paper. Can one prove that there is a threshold for R, or even better, can one nail down the explicit leading constant for this shotgun problem? To be honest, when I suggested to Haoyu Liu, who was a student in my class, we didn't hope to solve it because it looks quite difficult. Things on the lattice, we don't know how to do it. But you want to give students something to think about, and then read and then think, so that they can have a flavor of what research is. And in this case, I think we were lucky. It turns out, if you push the ideas that Mossel and Ross did in their paper, with some, I think we should give some credit to us. You need some clever ideas so that it can push down to the threshold. So let me first describe you the results, why it's already showing the slides, and let me tell you what is the additional ideas one need. And there's something that I feel we actually feel proud of. So we get for any D, we get the correct threshold for this recovery problem. But you see, there is already something interesting going on. There's a difference between dimension 1 and dimension 2 or above, because you see the two formulas. If for dimension 1, if we plug in the formula, if we use the formula for on the last line with D equal to 1, they are not consistent. This is roughly coincides with the fact that population has a phase transition in 2 dimensions and above, but does not have a phase transition in 1 dimension. And that also suggests how we can do the recovery. Let's look at 2 dimensions and above for the discussion, because these are more interesting anyway. 1 dimension, the result is actually not new, or part of it is not new, at least. Probably it's just not new. I forgot. The real meat is in 2 dimensions and above, but the comparison is interesting. So the idea for the recovery is basically what Erdos and Nathan did is they want things to be unique everywhere. They want every box to be unique and then perform the algorithm. Then you have to take a unit bound. We make this a bit more relaxed. We say, okay, we just choose the threshold so that a typical R box is unique. That already allows us to do quite a lot, right? We cannot determine everything yet, but we can determine most of the things. Even better, you can things would percolate, because you start with some R box, since typically an R box would be unique. And once things are unique, you can you can propagate, then you know what to stack on this box. You know how to patch two boxes together once things are unique. Then this naturally generate some sort of population picture. Start with the source, since things are good with a very high probability. And when things are good, you can determine the labels on those places. Then the phase one is you just, okay, determine those boxes that can be populated to. That's almost everything except you have holes here and there. Those holes are very subcritical, so things are very local. And then the remaining question is to, okay, from the information around the holes and from additional information from these local boxes, let's correctly recover what happens in those holes. Those take some work. I will not explain here because I don't think I'm able to explain these things in the talk. It involves some technical calculation, but you got the idea. Once you see that the population is the right thing to do, I think what remains is diligence and patience. There's no superb, clever ideas afterwards. And then we need to prove the matching, matching non-identifiable threshold. We need to show that if I is small, then we cannot recover. Our idea is the same as theirs. We want to find two local neighborhoods so that after some swapping, the global thing changes, but the local profile remains the same. But we want to do it for a larger R. So this actually is not at all easy. For a while, we thought this would either be impossible, or in order to solve it, we have to write many pages to do the calculation. Naturally, to show existence, we need to do a second moment computation, but the overlapping structure here seems to be daunting. Somewhat interestingly, this overlapping structure actually in this particular problem helped us to cook up a second moment that just basically imply the result without too much technical computation. So that's the idea. I didn't give you the exact second moment method, but that's because the main focus for today's talk is actually on the Erdős-Rényi graph, which I want to explain some other intuition to you. So I will stop the discussion for lattice labeling model here, and we'll move to the shotgun problem for random graphs. Let's first talk about random regular graphs, say with a fixed degree. As a consequence of the work of Belabash in the 80s, one can determine the asymptotic threshold for this shotgun problem. In a more recent work by Mossel and Sang, and Mossel and Nike Sang, they proved something fairly impressive. They get very precise estimates for this threshold, and it's precise up to additive constant. Now let's think about what is the philosophy that it drives the shotgun threshold here. Here is a quote from the paper by Mossel and Sang. In random regular graphs, tree neighborhoods are all alike because they are all just regular trees, right? If you only see regular trees, you don't get any information. It's just like that. So you have to go beyond the trees. And luckily, every non-tree neighborhood is filled with cycles in its own way. So in order to identify the whole graph, you really have to investigate and take advantage of the cycle structure in the neighborhood. If you don't see a cycle in your in your local neighborhood, there's no hope. And that explains why the asymptotic threshold is like log n over 2 times log d minus 1, because this is the threshold for the local neighborhood to have volume root n, and we know that's the critical threshold for us to see cycles in a typical neighborhood. So that at least that part of the intuition, I think we should be able to come up with. Well, as for Mossel and Ross results, how to get this additive log n and additive constant, I think that's harder. I don't know how to explain. Actually, to be honest, I didn't read their paper yet to get this out from. I think this would require some very careful examination of what happens with these cycles. And it seems their paper employed some rather involved second moment computation. But I'm happy to for the purpose of the talk, I think we probably can be satisfied with the intuition for the asymptotic threshold. That's because we want to see cycles, and once we see cycles, we get a lot of information. Okay. Now let's look at the Erdős-Rényi graphs. Well, this is probably the simplest random graph model, where each pair of vertices is connected with probability P independently. It's kind of like a random graph without any structure, but it has been studied so much. I don't know how many papers are there in total about the Erdős-Rényi graph. It's probably in the magnitude of tens of thousands of, I don't know, it's huge. So we are going to talk about the dense case and the sparse case, but before doing so, let me emphasize, dense and sparse, those are descriptive words. They don't have accurate mathematical meaning. What dense means varies with the context. Sometimes dense means P is a constant. Sometimes it means P decays polynomially. In our case, let's say it's dense as long as Pn is larger than log n square over n. So it's the average degree is like polylog n. This could very well be the sparse regime in some other random graph problems. Okay, and it was shown in the paper by Heng and Nathan that in this case, if we have observations for local neighborhoods of depth 3, then we can recover the original graph. Afterwards, more papers have been written, and people seem to be very obsessed about the question of whether one can recover the whole graph with a depth 1 neighborhood. Here are the results. It seems for this, we pretty much know it. If you are happy with some errors like polylog n or something like that. But it remains open if you take any power. If Pn is n to the minus alpha for all alpha, presumably there should be a threshold, there should be a number which corresponds to the shotgun threshold. That's still open. What I do want to emphasize a bit is in the paper of Galton and Mossel, they have the technique of proving non-identifiability, which is a bit different from the original paper of Mossel and Ross. Because I described to you a strategy that if we can make some switches or perturbations so that the global graph changes, but the local profile remains the same, we cannot identify the original graph. Or mathematically, it means if there exist two non-isomorphic graphs with the same empirical local neighborhood profile, the problem is unsolvable. And that's one way for the proof. I think this method based on Shannon entropy is a bit different, and it seems to be useful in many of the probability problems. It's kind of using information theoretic type of technique sometimes can be surprisingly effective. The idea is very simple. It's a proof by contradiction sort of argument. Suppose you can identify. That means if you give the local neighborhood, you can get the whole graph. If that happens, that means the entropy of the whole graph should be bounded by the entropy of the local observations. And then you just do computations about the entropy and find that that's a contradiction. That's false. Then one is not. So this kind of calculation is something I think we can probably take home. And when we encounter a problem of this type, maybe think a bit of whether information theory type of argument would be helpful. At least from my perspective as a probabilist, the original approach in Mossel and Ross paper is more natural. I would think about that too. But for this method of using entropy, it's less natural to me, probably also to us, but this is certainly more natural to a different community of people. So that's the kind of the underlying reason why I spent a few minutes here. Now let's move to sparse random graphs. And actually, let's say we look at Erdős-Rényi graphs with the average degree fixed as lambda. And in their original paper, they prove that if lambda is not equal to 1, then the graph is identifiable if I is larger than c times log n. If lambda is 1, then the result is not as good. They get a n to the 1/3 bound. Here the reason is not hard, because basically when lambda is not equal to 1, then all the components have diameter bounded by a constant times log n. In the subcritical case, they're pretty much trees, so it cannot be too large. In the supercritical case, there's a giant component, but the giant component has diameter log n. So if you can see neighborhood of a large constant times log n, you pretty much see everything you want to see. And I think the more interesting bit from the paper, sorry, I hope Nathan will not take this as an insult. The more interesting bit in their paper, which is quite inspiring, as we'll see later, is the other side. They show that GMP is not identifiable if I is a small constant times log n, and I will explain what they did here now. The proof is based on a second moment argument to certify existence of a certain blocking subgraph. The blocking subgraph is very similar to what I described for the lattice labeling models. Find two neighborhoods with a certain structure, and we want to swap what happens in the center. This is the same philosophy. What they say is, okay, here is a blocking subgraph. Why is it? Because suppose this is induced subgraphs. You can find such induced subgraphs in the GMP. Now change these two subgraphs from the left-hand side to the right-hand side. We are not change the R neighborhood. That's because every vertex, their R neighborhood remains the same. You have a straight line of 2R length, then it does not see this. I don't know how to describe this in English. It doesn't see the difference when you move this green stuff. When you put this two green stuff in a single line or into two lines. But clearly, the graph is changed because the 2R neighborhood is different. So that's what they did. And well, the first instinct I saw this is, wow, this is clever. The second instinct, I'm sorry, Nathan. Okay, maybe one can do better because why this whole thing of length 2R should be a straight line? That construction seems to be too restrictive. if we allow more freedom, more flexibility on how this middle part of line 2R look like, we can allow a larger class of blocking graphs, and as a result, this should give us a better bound, right? So that's what we did. Oops. I think these 2 slides maybe, oh, right. That's what we did. And before I tell you what we did following this idea, I will tell you what the result first. So this is joint work with, the first work is joint with Haoyu Liu, and this one is joint with Yiyang, Jiang, and Heng. I think Haoyu and Heng were in the audience or are in the audience, but anyway, they are very pleasant to work with. So we for a lambda, fixed lambda, we first define some parameter gamma lambda. This is the probability for 2 independent rooted Poisson Galton-Watson trees to be isomorphic with each other. So basically, there is a root preserving bijection between the 2 trees, which also preserves the edges. And what's the probability? This probability should be a constant, right? Because there's always a probability. I mean, this probability, of course, should be a constant. In particular, if both trees just die out in the first step, they are isomorphic to each other. Then we can determine the shotgun threshold explicitly, and this threshold is written in terms of this isomorphic probability. Of course, since I wrote it this way, it implies that the lambda square times gamma lambda is less than 1. This is not hard to verify because the isomorphic probability is less than the square of the extinction probability, because it's easy to see that if 2 trees survives, then they should not be isomorphic with each other. Okay. Now I need to explain to you why the isomorphic probability takes into the picture, and also why we feel that we observed something that seems clever on top of what Nathan and Heng did. You see this structure of this blocking subgraph? Let me show you what happens in this slide. It's a complicated version of what they did. In the middle, we put in not 2 straight lines, but kind of 2 straight lines. These are the red points, but we allow small subtrees decorating, hanging to this straight line. Okay, or more precisely, we want the middle part to be 2 trees of height 2R that are isomorphic to each other. And in addition, if we remove all the red points, what's left are just small components. Okay, and on the bottom, we have one of them is CU, one of them is CV. They're just different. They are not very important, as long as they're different. Now on the top, we have a green line that is of large constant long. This serves as the sort of the green stuff here. What we want to do is, if we move this green part from the left to the right-hand side, oh, by the way, I should say that when I say this is a blocking configuration, I mean in this graph, we can find 2 induced subgraphs like this. And then if we move this green part from the left-hand side to the right-hand side, we see, using the same philosophy of theirs, the R neighborhood remains the same, but the graph is changed because, well, you can just look at the maximum diameter of these two subgraphs. When we move the green part from the left to the right-hand side, it's changed. So this changed. So what remains to show is the probability for us to find such blocking configurations. And this basically boils down to, let's look at two fixed vertex u and v. What is the probability that u and v actually giving us a pair of blocking configurations with them being the roots? Then this naturally calls for the calculation of the probability that the two parts are isomorphic, right? But this is actually a bit different from the two trees to be isomorphic. We want the two trees to be isomorphic to each other, but also we want the tree to survive for 2R levels. They cannot die out, right? They have to survive for 2R levels. So there's a bit difference between just the tree isomorphism probability, but they are connected. Also, we want to put some additional constraints that after removing the red points, all the other things are small, so that for instance, we want the other components, the diameter is smaller than the length of my green part. We need that to verify indeed this is a blocking configuration. If you didn't quite see that, that's because I put some of these technical things under the rug. But anyway, so now we should look at the probability for tree isomorphism. But what we want exactly is the isomorphism and the survival. We define the probability P sub R to be the probability that the two trees survive for at least the R levels, and also the first R levels, they are isomorphic to each other. Well, the key input is that this probability decays exponentially. And also we can actually compute the decay rate in terms of the isomorphism probability. We don't know how to, by the way, we don't have explicit formula for the isomorphism probability. It would be nice to have it. We don't know how to do it. We are not sure it's possible. But anyway, we have exponential decay here. The above is proved via induction argument. It's not that hard, but it's not particularly pleasant or inspiring to show it to you. And in addition, we have the input that condition on that two trees survive and also isomorphic. Then if we remove this ray of length R, what remains should be small. This is kind of intuitive because you see, we have exponential decay of probability for things to survive and be isomorphic. That means if you want to survive and also being isomorphic, better just survive in a single ray. Once you have a single ray, you have already fulfilled the requirement that you survived. Now, in other places, the optimal thing you can do in order to be isomorphic is to die out quickly. Because if you in other branches, if you also survive for a long time, that would be very difficult for the two trees to be isomorphic to each other. So in a sense, what Echner and Nathan did is in the other branches, they just simply say they die out at the very single step. That certainly kills a lot of probability because what happens in the first 100 steps still has, we still allow a lot of flexibility. And that flexibility allows us to control this probability in a better way, which gives us the threshold. Okay. So yeah, we feel we did something, and then we wish to prove that near this threshold, we can, I mean, if you cross it in the desired direction, then we can actually identify the whole graph after isomorphism. There is a key puzzle. There is a lot of technical work actually, but I just want to explain the key puzzle here. Well, it's not the key puzzle in terms of the whole proof, but it's the puzzle that I feel you may be wondering now, because in constructing blocking configurations, we use neighborhoods of depth 2R, right? How can this be consistent with the R neighborhood in our local observations if you want to use things to for identifiability? The answer is not that hard. Essentially, we only care about vertices which have two disjoint R arms. So these are nice vertices. Since any vertex without two R arms, you think about it, it's either in a small component, then you don't care about it, right? because those small components can be easily recovered. You take one vertex that kind of is in the center, then the local observation gives you what happens in this component. Or this vertex is contained in an R neighborhood of some nice vertex. Then you can identify or you can recover this non-nice vertex from the neighborhood of the nice vertex. Okay. Then the next observation is the probability for two Poisson Galton-Watson trees to be isomorphic with two disjoint R arms. Well, that's like isomorphic with one arm. You have exponential decay. Now you want to have another arm. Okay, the square of the exponential decay. That's actually pretty accurate, and it's not hard to show. So this is, since we have exponential decay, then this is exactly the probability for two Poisson Galton-Watson trees to be isomorphic within two R arm, which is the construction we used in the non-identifiable regime. That's why things are consistent. So there's no missing of factor 2 here. Here's a caveat. In all these discussions, we treat things as trees, right? This is also the difference in the driving mechanism from the shotgun problem of random regular graphs. For random regular graphs, the cycles is the key. But for Erdős-Rényi graph, the trees already look different enough. We don't need cycles. But we don't need cycles doesn't mean cycles don't show up. We still need to deal with them. We have ignored cycles in our R neighborhoods. This is conceptually fine because some computation says that our critical R, at our critical R, every neighborhood has volume less than √n, so typically it's still a tree. But technically it incurred some serious challenges. It's sort of like the population idea. You want to start with the good things you can determine, and I mean the population idea we used in the lattice labeling graph, but here it seems just harder and incurs substantially more work to deal with this. But I think it's kind of convincing because most of the things are trees. You first identify those parts, and then you try to deal with what's left, more or less. One has to show a certain of things, a priori structure results about the Erdős-Rényi graph, but that can be done. Okay, and it's time to finish my talk with some perspectives. Hopefully I didn't have well, if I didn't succeed, you can ask Nathan that. I think he can convince you that this is a good set of problems, rich in theory and applications. One interesting direction, as I mentioned earlier, is to formulate, okay, there's another typo, mathematical models from important applied scientific problems. That actually adds a lot of interest from biology. I heard a talk by from someone who works on sort of biostat, and they actually do a lot of shotgun sort of problems in their study. It would be very interesting to formulate some nice mathematical models which is closer than the one we study here. And another very interesting direction is, what if observations are with noise? So far we suppose that all the observations are perfect, but that can't be the case in the ideal world. So in the case that the observations are with the noise, either we have to be more modest to be happy with a recovery that is cracked almost, but not exactly cracked, or we have to have repeated observations so that we can do sort of majority vote to recover the truth or something like that. It's not yet clear how to formulate these problems more carefully. One can do some formulation. We tried a bit. There are various directions, but we don't know which ones are the most interesting to go. Certainly, in general, this would be an interesting direction to go. Also, you want to go beyond IID models. You want Erdős-Rényi and lattice labeling models. So far, it's more like IID, but we would like models that is more realistic, but it's unclear which graph models or which labeling models would be more interesting than the others. Erdős-Rényi and the IID uniform, those are canonical choices. Maybe one can try random geometric graphs or things like that. That's also a good direction. There is also the algorithmic perspective. For both problems in the identifiable regime, we do have polynomial time algorithm to do it, but we don't have the most efficient algorithm, especially for the Erdős-Rényi graph, sparse Erdős-Rényi graph recovery problem. So far, our algorithm has a polynomial time with a pretty bad power. Maybe things can be much more efficient, and that's also interesting because computation is non-trivial these days. Okay, I think, oh, the timing seems to be perfect, right?
Yeah, all right, thank you, Jian.
Thanks for your attention.
Do people have questions, comments?
Yes, I have a suggestion for further problems, as it were. One of the things that's interesting when you have a collection of different graphs is to try and work out which ones are similar and which ones aren't. And one of the sorts of information that people compute is looking at these neighborhoods, but not necessarily taking the whole neighborhood, but just some characteristics of them, like how many small subgraphs of different sorts do they contain. So, so there seems to be a whole practical use to looking at information which is less than knowing the structure of the whole neighborhood.
Right, that's a very good question. In all these models, we just gave you all the information about this local neighborhood, but certainly you can just give me some features about them, right? And depends on the application, then you can decide which are the which features are most relevant. Actually, for instance, for the random regular graph, I just said Bellabash's result says you can get this from this local neighborhood, but I think the distance, pairwise distance there may already be enough, if I remember correctly. So things like this certainly are interesting directions to go. It's just like, what are the most natural questions you want to ask? That's unclear to us, and we don't have infinite amount of energy. You can choose, for instance, degree distributions or distance profile, or there are many choices, right, to describe. If there is, so that's why I said if there's a particular important applied problems one has in mind, either from social network or from network in physics or biology or chemistry, then you can see, okay, for this problem, this particular choice of features is most natural because that's what's available in the lab. If that's the case, I think that would trigger more study. Otherwise, I'm feeling there are like 10 equally interesting problems. Which one shall I go to? I mean, in this case, you just feel, okay, I will wait until someone tell me what to do. For what we did, these are kind of very natural. It's like, okay, this is the most natural thing to do. That's why we did it. Or that's not we did it. That's why they studied this problem in their original paper. They have some other examples like jigsaw, which I didn't describe. That's basically the situation.
Yeah, I have a related comment, which is like in the DNA shotgun problem, like you can assume either all the reads are the same length, but actually that's not very realistic. When they do the chopping up, the reads are actually of different lengths, right?
Sure. Yeah. So right.
You could do a similar thing here, where the neighborhoods are of a random size, or something like that.
Right. You can make the size of box to not be constant. Sure.
Yeah. Presumably, if there is an application where they have data, it's not going to be exactly.
Right. Actually, here it's an interesting question: is whether the expectation, what it's probably not the expectation of the radius, maybe it's the expectation of the volume or something of the distribution matters. It's unclear.
Yeah. It's not clear. I don't know. It's not clear if it'll be some universal, or if there is exactly what that will be. So I think that's kind of an interesting thing. But
right. I mean, you can also incorporate spatial information for the DNA, right? Except for the ATGC sequence, the DNA itself has a spatial structure, but it's unclear how one can model that.
Yeah.
It's like a self-avoiding path in 3D, but okay, I think if you start with that, I'm down. Not good. One has to find a nice, natural, and accessible distribution for the DNA. You need some prior distribution, but we don't know what is good one. But I think people care about that too. What is the spatial structure of the DNA?
Yeah, definitely.
We just don't know how to formulate. I think for this, we need engaging mathematicians and also engaging, say, biologists talking to each other in a relaxed manner. They like meet every week, just having a cup of coffee without a concrete idea of writing a paper anytime soon. But at some point, oh, this is actually a good problem to work on. I tried to do that, but apparently I'm not very patient, so I haven't been successful. I'm waiting for someone else to tell me, hey, we talked for 2 years and here are the problems I think that are meaningful and probably interesting. Maybe Nathan can do that for us. Yeah, that would be great.
I have one more question, but is there anyone else who has a question? No. So in the lattice problem at the beginning, you assumed and we did too, that the labels were uniform. But did you think about if the labels aren't uniform? Because I think the problem's a bit harder then, because if you know 2 of the neighborhoods are different, you've learned something about their labels in the non-uniform case.
Right.
Because there's more likely configurations that make things different, so it makes it a little bit more difficult. Actually, that's what I remember when we were working on that.
Right.
That's why we ended up doing uniform.
Right, that's a good point. We didn't think very carefully about them. At least I feel if you still have independence, one can still try to do the computations. I don't know at which point you will find, something non-trivial occurred.
Yeah, it's like, I mean, even if you do the second moment and you're just counting the number of unique neighborhoods and stuff, you get, somehow the covariances are a little different or something like that. That's all I only vaguely remember this.
Right. It may depend on how singular. If the distribution is not uniform but has a lower bound on the probability, maybe it's doable. Yeah, we didn't think very carefully there. We did try to think about, say, what if it's a measure, and then okay, it seems independence is.
That's even getting a little bit more difficult.
Right, some of the calculations we stopped being able to do. So, and also nobody told us is a measure is particularly interesting, so we stopped. For these questions, it would be really good if someone tell us, look, this type of measure is of particular importance. So far, we didn't quite see that, and each of them takes effort. So yeah, these 2 papers took us actually quite some effort.
Yeah. No, they're nice results, and it's a very nice talk.
Okay.
So let's thank Jian again. Yes.
Thank you for your attention.
Thanks, Jian. It was a great talk.
I'm very happy to give the talk. It's very relaxed.